Okay, I'm Zhongcheng Yang. So today I want to present my recent study about the investigation of the complex magnetic behavior of the spinel material Fe2008. Well, actually, it's a chemical formula should be Fe 1.5 or 1.504 in typical spinel structure. I will explain that later. Okay, so this is my outline. So in the beginning, I want to present, I will give you a very short introduction about this system. And then I will show the sample characterization. And we also measure its thermal properties, including specific heat. And magnetic property we will also measure. So we have magnetic susceptibility result, hysteresis loops, and neutron magnetic scattering. And finally, I will show you something a little bit different. We practice energy gap, which is spin optical carbon gap, by using the inelastic neutron scattering. Then we will give you a conclusion. So this is a typical spinel structure. In the spinel structure, there are tetrahedron and octahedron. So in the tetrahedron side, typically we call it the central ion is called the A side, and for the octahedron side, and the central ion is called the B side. So if we put the divalent ion in the A side and the trivalent in the B side, we call it the normal spinel structures. In contrast, if we put the trivalent ion to the A side and divalent ion to the B side, that we will call the inverse spinel structures. For the spinel structures, we know the A side and the B side was arranged alternately along the crystalline. So this is the typical spinel structure. Okay, in these structures that have fluid properties, it's a little bit complicated because if we use the transition method which contains 3D electrons, that will give you very complex properties. So in these systems, they have some crystal structure change or crystal phase transitions. So they will have a degree of freedom in the crystalline. And if in this system, you know you have divalent and trivalent ions. So if the charge is nearby, crowded nearby the A side, B side, even O side, they will have a charge order. And if the bonding or their orbital arrange some specific pattern, they will show the orbital order. Of course, they have different spin state, so they may order with spin order or called magnetic order. So these four properties was interacting with each other, so that's a very strong correlation systems, and they create this complex physical property. So this is an article review. In the typical Fe2004 system, they have four different crystal phase transition. From the low temperature to high temperature, at the low temperature, the firstly they becomes tetrahedral phase in the C larger than A state. Then it transferred to the orthorhombic phase and come back to the tetrahedral phase. But in this stage, the tetrahedral phase has AX larger than the CX. Finally, if we go to the temperature up to the 110K, they will become cubic structures. So this structural change will also influence its magnetic properties. For example, if you look at the susceptibility curve, this is the inverse susceptibility curve, and this is the Biot and the Biot curve. You will find that at the high temperature up to the, if we're going down to the low temperature, you will find this paramagnetic phase and transfer to the ferro or ferromagnetic phase and become a little bit anti-ferromagnetic phase. And this turn point can correlate with each phase transitions. Of course, if you want to mention about what is the phase transition, you need to measure the specific heat. So there is four anomalies from low temperature to high temperature, and that can correlate with those phase transitions. And there's one more thing: if we measure its saturated magnetic hysteresis loop, we will find at 5K the saturation magnetic moment is 2.15 4 menon per 4 menon unit. And there is a magnetic loop, which means that there is a magnetic domain here. And we can also test that with the AC signal. So if we do the AC magnetic susceptibility, we can confirm that they have something change at the 110K. And one more thing, particularly one more thing is, if we apply the magnetic field, we will find the dielectric constant change with the field, with the strength of the field. So that means in this system they have a magnetoelectric interaction. So actually, its phase diagram already studied since the 1963. So in my systems, I just mentioned about it. If we can write it in another form, is Fe 1.5e 1.504, which means my system is at the x equal to 0.5. So in this phase diagram, we can expect we have a two phase changes from the tetragonal to the cubic. So let me check everything is like identical to those reports. But I don't want to repeat some research like others, so we found something interesting that I will talk about later. So in another different experiments, they did inelastic neutron scattering and found there is some spin orbital interaction gap here at the roughly 9 MeV at the 3.5K, and it was suppressed by the temperature as the temperature up to the 110K. So in this pure FeV2O4 systems, we know its spin orbital cap would be eliminated by the rising temperature. And this is the order parameter of the this gap. Okay. So that's the article review. And in my system, firstly, I need to do synthesize this sample, right? So actually, this study started from I do another research. So I have my colleague, they did some ion batteries for the solid electrolyte. So this is one kind of a solid electrolyte. And I found, okay, they have a 3D transition metal, maybe they have some magnetic properties. So I just borrow the sample and do some tests. So the first thing, they did the sample with the x equal 0.5, right? So I think, okay, there's no one reports such kind of system, so I just study that. So this is the reason I use this chemical formula, because in the chemical field, they use this non-metallic compound name, okay? So they did, actually this is I did this sample with the, I did this sample and the test is structure with the X-ray diffraction. So I define structure that would be from cubic Fe minus 3m phase at the room temperature. And then I think, okay, we need to test its specific heat if they have three phase changes. So I just sent a sample to National Cheng University professor from Zhenong's lab. So he gave me this curve, and we found there are three small anomaly at the 157, 187, and the 222K, which is totally different to those reports. And these peaks are so tiny, so we need to plot the C over T and the T product. Of course, this typically you can know is C over T to T product. You can integrate in the area and get the entropy. But let's tell you, there is some tiny phase transition, some kinds of phase transition that is irrelevant to the magnetic, because they apply the different external magnetic field. And we also test the typical magnetic properties. So we have a field cool and zero field cool test. So we apply 100 Oster magnetic field. We found, okay, its magnetic must be higher than the 400K. Using the limit of the instrument, so we only know the temperature will be higher than 400K. Of course, we needed to know if there is some magnetic cluster. So we also test the AC magnetic susceptibility. we found that if we increase the frequencies, that the peak intensity will suppress. That implies that may be formed as magnetic cluster. Okay. And we also did a hysteresis loop that saturation magnetic moment is 2.26, which is close to the load report. So the most important is if we want to explain everything, include those previous report and my study, we need to solve this magnetic structure. So I do the magnetic neutron powder diffractions, and okay, the time will up. So I just show you. Okay, we found that the magnetic structure at the low temperature 3.3 K is the I41 AM prime D prime. And going to high temperature is the cubic phase with the magnetic structure FD minus 3M prime. So this is the evolution of its magnetic structure at the low temperature 150 K. So those magnetic structure is tetralike. But up to high, and the temperature up to the 300 K, they are formed in the cubic phase. And there's one thing interesting that the B side, the magnetic at the B side disappeared. They only left the A side. So this is the sketch of its magnetic moment and its crystal structure. So they are highly correlated. So this is the spin gap test. That's one thing very interesting. For those reports, they claim that the spin orbital gap would disappear at 110 K, but in my case, this gap is survive up to the 300 K. So they must be tell you the spin orbital coupling would be stronger than those ever report. So I think that there's something interesting, but unfortunately we don't have enough time to explain the detail of that. So let's just show you my result. So this is the conclusion. So the crystal and magnetic structure of the Fe3B308 is characterized by the tetranol I41AMD and I41AM1D symmetry between the 1.5 K and 150 K. And its crystal size is FD minus M and FD minus 3M prime. Okay, its magnetic correlation comes at the temperature excessive for 70 K, and the energy gap is induced by the spin orbital coupling, and it's quantified at 6.8 MeV. Okay, there's still something we need to pay effort to understand why they have such strong spin orbital coupling. Okay, so I want to thank those lab to give some help. The most important thing we got acknowledgement to the National Synchrotron Radiation Research Center, and most importantly, the National Science and Technology Council. Thank you for your attention.